Yeah, okay, thank you very much. Yeah, so today I will be talking about the toolkit, kind of following on from Barry's talk earlier, giving some actual examples of it in use. I'll just briefly remind what the toolkit is and what its goals are. I think that's really well summarized by this paragraph here on the webpage at bhptoolkit.org. And the goal of the toolkit, just like with the Einstein toolkit, is to really reduce the amount of time spent writing code and more time doing physics. So the reason the toolkit came into existence is about 2015, 2016, we realized that there are, people have been writing, for instance, Teukolsky codes. They've been writing them since the 70s, basically. And yet, even in 2015, there were no publicly available Teukolsky codes. Everyone who wanted to solve the Teukolsky equation went ahead and did it themselves. They wrote one new one from scratch, or at best they borrowed one from a colleague who'd written it before. And so that kind of birthed this idea that what we wanted to do is to bring together some of the core elements of those codes. We're not asking people to give up the latest and greatest codes necessarily, but bring together some of those core elements into a toolkit that can kind of reduce the amount of time people spend actually working to solve coding to solve perturbation theory and more time doing the physics calculations. Yep, okay. And so I thought I'd start by just quickly going over the website. There's some useful things here to note. First of all, just to point out, and I think Barry mentioned this as well, that the toolkit's been around a little while now, and it's been used in quite a number of papers. So we have this webpage here, which shows the contributors and users as they appear all over the globe. And at least as far as we're aware, there are now 84 papers that have actually cited or acknowledged the toolkit as being important in their work, or cited packages that are in the toolkit for reference. So it seems to be getting some good uptake, which is nice. Something else, of course, that's very important for software toolkits is documentation. So we'll look at installation in a moment, but you can find some information about that there. Each module does have documentation. As I'm sure you know, in your community, it's extremely hard to get people to write documentation. It's boring but important work. So it varies in quality from place to place, but each package should come of its own. And today I'll be giving a little tutorial about how to use some aspects of the toolkit, but the toolkit is much broader, has a much broader range of packages than what I will explore. And so if you are interested, a good place to start is on the toolkit YouTube channel, where we actually recorded, again, as Barry mentioned, the 2020 toolkit workshop ended up being virtual because of the pandemic. But the upside of that is it was all recorded. And so an overview of all the packages can be found there if you're interested. That's a good place to start. And finally, on this page, if you're ever curious about naming conventions, we try and be consistent across the toolkit. The toolkit's made up of many individual packages. They don't necessarily interact. We do try to be consistent, and we have a selection of naming conventions. So for instance, we always work with geometrized units. This is the metric signature we always use. In general, we will refer to the mass of the primary by big M, the spin of the primary by little a, and so on, and everything is a-dimensionalized. So those are some useful things, and we'll see some of that as we go along. The main part, or the most useful bit, of course, here is actually the list of all the different projects, all the different packages. At the moment, these are separated by the language that they're written in. We've had some discussion about whether that's the right way to do it, but here it is. There's a fair amount that's done in Mathematica, just because a large portion of our community works pretty heavily with Mathematica calculations. It's great for prototyping calculations, obviously not great for producing vast quantities of data. It's not that fast. There are some projects in C and C++, and there's also Python projects and some connections with SageMath, as well as Fortran. At the top here, all of these are software packages, but the toolkit also contains data that can be in different forms. It can be numerical data, or it can be analytic series. There's a lot of very large equations that are produced by the community, whether they're very high order Post-Newtonian series or these regularization parameters that are useful for computing the self-force. They're often too big to actually put explicitly in papers. Otherwise, you just have a 30-page appendix showing, one very large PN series. And so this is a way, and we'll look at that today, about sharing some of these analytic formulae. Also, it's worth saying you will find here some examples. So again, I will just give a few examples here today. If you're working through various other packages, particularly mathematical ones, there's a whole load of notebooks there that are quite useful, showing how to use the packages to do various little calculations that you might help you learn how to use them. Okay. And yeah, as Barry mentioned, if you do ever end up using it, then of course, please do cite the toolkit in this simple way. At the moment, that's all we have, but it really does help us keep track of who's using it, because you can basically just Google this sentence and you'll find all the papers that have actually acknowledged the toolkit. So it's very useful. Okay, so in terms of the packages today, I'm mostly going to be focusing on a few of the Mathematica packages. And the goal is to compute some waveforms. We'll do a comparison with a numerical relativity waveform. We'll discuss how good that is and how you can do better in the future. But I will also show one Python package, this one that Barry mentioned in this talk, this Fast EMRI Waveforms package. This is sort of being positioned as the package that will be used in the LISA data analysis eventually, or some variation of it, for producing EMRI waveforms. And as we'll see, we can produce, in this tutorial, hopefully, we can produce year-long waveforms in a few seconds on your CPU, or in fact, a few tens of milliseconds if you have access to GPUs. So it's a very nice and very modular piece of software. This one to install is a little bit more involved. So if you are particularly interested in that, I recommend you sort of take a look at that now if you haven't already. If you go onto the page and click Get the Code, it'll just take you to the repository. And then the README file, I think, is very clear. It has the instructions that Barry showed earlier. Assuming you have Anaconda, you can just execute these commands and install the package. I did it this morning to make sure everything worked, and it was all very smooth. So hopefully it'll work well for you. So that's that particular one. But for Mathematica, it's actually very straightforward. If you pick on any of the Mathematica packages, all of this software is packaged up in these things called packlets. So when you click install this package, you're taken to this page that tells you just the general way you would install any of the Mathematica packages from the toolkit. That's by adding our Packlet server to your Packlet site register. Note there's a slightly different way of doing this in Mathematica 12.1, one of the latest releases, or earlier. It's just slightly different wording. Packlet site register versus Packlet site add. Why they changed that. But once you've run these commands, you can then just install all these packages very quickly. And then if you run this command again later, it'll update the packages automatically for you if there's any new releases. But we'll go over that in the beginning of the first notebook that I'm going to look at. Okay, yes. So as was mentioned, you can go onto this piece of the timetable for the workshop. And there's these additional files. I'm going to be working through these. There's two called solutions, which are the complete versions, which if you want to just have those for reference, whereas this is the kind of empty version that I'll be filling in as I talk through the various bits of software, basically. So I'd recommend using this, but then the complete version, especially if I don't get through everything, can be found here with all the examples, and the same for the Python code. Okay, so assuming you've got those, I will just share my screen for the tutorial. Okay, just sort out my Zoom windows. Okay, hopefully that's the font size is okay. I've made it slightly bigger, but if anyone makes it larger, just let me know. And I can do that. Okay, so as I said, the first part of the tutorial is going to be looking at the Mathematica packages and what we can do with those. And the goal is to compute waveforms in various different ways. We will first look at installation, but then we will look specifically at the Kerr-geodesics package, which is sort of the base for many of these things. If you want to compute the gravitational waves, you need to tell it for which orbit. So we'll take a quick look at that. Yeah.
Yeah, could you increase the font size just a little bit? It might be.
Yeah, no problem at all. Is that better?
Yes, that's better. Thank you.
Great. I'll just. Yep. So want to compute some waveforms. So we'll look at the Teukolsky package, which, as its name suggests, solves the Teukolsky equation. Just a few simple commands. We'll then make a comparison to a numerical relativity waveform computed with the Einstein toolkit. As you might expect, just using linear perturbation theory, that does okay, but not that well. I will briefly then mention that actually a lot of work has gone into recently doing second order in the mass ratio calculation, so extending perturbation theory beyond linear order. And quite remarkably, that seems to do quite well compared to numerical relativity. Now, the toolkit does not contain any software for you to do that as yet, but over the coming year, our plan is to open up a large portions of that software into the toolkit so that other people will be able to make those calculations as well. Those calculations are significantly more involved than first order calculations. They're not yet at the scale of numerical relativity calculations, but they are creeping in that direction, let's say, and I'll discuss that a little bit later. And then I did really want to show as well, some other bits of the toolkit, particularly some of this sort of data side of things. And one of the nice packages that I actually find I use quite a lot is the ability to load PN series. So we have these very high order post-Newtonian series in self-force theory, like Barry mentioned, 22 plus PN. You're never going to type that in by yourself into a piece of code, and so that's all stored, and there's a package written around that kind of lets you load those and manipulate them, and then we can use those to compute inspirals as well. Depending on how time's going, this is a little bit more involved. We'll also do an inspiral for eccentric orbits, but if there is enough time, then I'll try and press on to the Fast EMRI Waveforms. That's a very useful package, very practical one for computing EMRI waveforms for eccentric or even generic orbits. Okay, great. So before we do any of that, though, we of course need to actually install the software. So if you open up the first section, you'll find basically exactly the code that was on the website that just installs the software. So let me just also make sure kernel is cleared. So this won't do anything for me because I already have it installed, but if you just run this, this should add the Packlet server. This second line here will collect the data from the Packlet server. And then finally, this last one will just install these packages. We're not going to look at general relativity tensors today. We won't be looking at spin-weighted spheroidal harmonics, though it is used, so it's important. We weren't looking at it explicitly. Again, it's a very useful package and was the very first package that was actually in the toolkit. And likewise, we won't actually be using Reggie Wheeler's today, but if you're interested in perturbation theory, you may as well install it. But we will be using all the others. So if you run that, again, for me, it does nothing, but for you, if you haven't got it installed, it will install those packages for you. Now, importantly, you don't need to run part one again, but if you want to update at some point, then you just run 2 and 3, and that will update the packages as new versions are released. Okay, great. So what we'll do is just crack straight on, look at the Kerr GD6 package. So as of all packages in Mathematica, you load them with the double arrow, and this one is called Kerr GD6. And it's crucial at the end when you're loading a package to put this little backtick, otherwise it won't load. It's just the Mathematica syntax. So I do Shift Enter on that, and if nothing happens, then that means it's worked, hopefully. With our packages, and as is very common with Mathematica syntax, the names are kind of quite verbose, and normally it's quite clear what they mean straight away just by looking at them. And in general, the packages always start with the names of the functions start with a piece of the name of the package. So the Teukolsky functions all start with the word Teukolsky. In this case, Kerr GD6 always starts with Kerr Geo. So if you look for Kerr Geo star, that tells you all of the packages that are now in your context that start with that. So you can see there's a bunch of packages for computing constants of motions. There's a sort of general function for dealing with orbits that I'll talk about. Computing the frequencies can be very important, and there's a bunch of special functions for dealing with things like the innermost stable circular orbit, or where's the separatrix and things like that. At the moment, the package only does time-like bound geodetic orbits of the space of Kerr spacetime. With one exception, there is one function here to compute where the photon sphere radius is, which obviously related to null orbits. Some of that is changing. There is already some code to do hyperbolic orbits in one of the branches. It's not yet merged into the main branch. And some code, I think, for null trajectories is also, again, in a separate branch that we merged at some point in the near future. With all these functions, there's a bunch of parameters that pass, and they're the same ones that were listed on the web page. Generally, we have the spin of the black hole varying between 0 and 1. So we always take the spin. I think this is consistent across the toolkit, but certainly here we always take the spin to be positive, and we vary between prograde and retrograde by changing the inclination angle. The orbits are generally parameterized by the P, which is a semi-lattice rectum. So it's not the semi-major axis, it's something slightly different. And the orbital eccentricity. And if you like, these are defined with these relations here between Rmax, maximum obtained radius, and Rmin. So Rmax is P over 1 minus E, and Rmin is P over 1 plus E. And finally, there's an inclination angle. Now, if you've ever looked at the literature on this topic, you'll know that there are actually many different definitions of inclination angles. This one is worth watching out for. There's one called iota, which is related easily to the Carter constants. Some people use theta min, some people use theta inc, and here we use the cosine of theta inc. So it's just worth noting if you're comparing to other calculations that are out there, to make sure when you say the inclination angle, you're talking about the same measure of the angle. This is what we'd use here. Okay, so as terms of functions then, let's just take a look at a few quickly. One I use very often is just the constants of motion. And so these functions, as often as possible, we allow them to be, where it is possible, to be analytically evaluated. But first of all, let's just take a quick look at some numerical values. So black hole spin of 0.9, semi-lattice of 0.2, 0.7, and some inclination angle, roughly 45 degrees, let's say. And that will return then the energy, angular momentum, and Carter constant, all appropriately eight-dimensionalized for that particular set of numerical values. With anything in Mathematica as well, you can work to higher precision if you want. So just by putting backticks here, you can work to arbitrary precision. And that's generally true across almost all the packages we have. Sometimes that can be a useful quick fix to your problem. It's just to go beyond machine precision. That can be useful. So for instance, the Teukolsky package later on, we see if you really want to know the fluxes to 100 digits, it'll do it, although reasonably slowly. The other thing that's worth pointing out, as I said, is that sometimes, not always, we do know analytic formula for these things. So in a simple case with Schwarzschild, so A equals 0, we set P and E, and then we just set the inclination angle to 1. And then we can actually get the analytic equations for the energy in terms of these other constants of motion, likewise for the angular momentum. What's particularly useful is when you look at Kerr, things do become much more complicated. So very quickly, the equations start to grow. And once you have fully generic orbits, Mathematica actually recognizes it's so large, it doesn't want to show it all to you. These are very big equations, but they're all analytic. And so if you want to take derivatives with respect to various variables, you can just go ahead and do that. So that can be pretty useful. Another useful function, particularly when everything I'm showing today is going to be calculations in the frequency domain, you need to know the frequencies associated with the orbit. So the function for that, Kerr geo frequencies. You can pass it again a bunch of parameters, and it will return the frequencies. So here's the radial frequency, the polar frequency, and the azimuthal frequency. These are all defined with respect to, by default, with respect to Boyle-Lindquist time, but it can be also useful to have frequencies defined with respect to, say, proper time. So those are all coded in there as well. And then you see the symbol changes, so typically small omegas for the proper time. And there's also another one called Minotime, which is useful for separating the radial and polar motion of GD6 in around Kerr black holes. In this case, epsilon is the character used for those frequencies. Again, if you want, you can say, actually, I want to have this analytically, and it will actually give those analytically this time in terms of elliptic integrals. Okay. Probably the most useful function in the package is one that basically does this all for you and also gives you the orbital trajectory. And actually, this is something that's going to be needed to be fed into the later parts of the calculations. So the Teukolsky package will need this. So we can define what's called a Kerr geo-orbit. Again, we'll pick some parameters. And when you run that, this then gives you some object, in a sort of Mathematica sense, an object, a Kerr geo-orbit function that you can now query for various properties, basically. So I can ask for the frequencies. There they are. In this case, internally, it's computed the Minotime frequencies. It's the epsilons. And things like the energy and so on and so forth. They're all available there. One thing it can do that's going to be kind of nice is it'll give you the actual physical trajectory. So this will produce some ugly looking function. But these are returned then as the time, the radial motion, the theta motion, and the phi motion. So we can assign those to these symbols. So this is the TP, or you like the radius as well. RP is this one. Not particularly nice to look at, but more interesting to plot. So here I will just cut and paste the code for the plot rather than writing it all out. This is exactly the code that appears on the actual web page itself for the toolkit. I just noticed that's a different phi. Just change that. And you can go ahead and plot the orbital motion for a certain range of Minotime. And here is this case, a very generic orbit around a rapidly rotating black hole, which you can then manipulate in 3D. That's exciting. That's a complicated orbital motion. Now, what I will show you for perturbation theory, we can actually only do circular orbits in the toolkit at the moment, but that will be changing in the coming, I would say, 6 months. We'll probably expect our fully generic codes for computing perturbations with sourced by orbital motion like this, I think. Okay, so that's computing the trajectory. Just to mention, as I said, there are a few other useful functions that can be useful. So for instance, you might want to know where the ISCO is for a prograde orbit. That's what it is analytically. You may want to know, if you're looking at more generic orbits, there's this region of this parameter space, which is, you know, the orbits are bound, and there's region below that where the orbit will plunge or scatter. And the line between those is known as the separatrix. Again, sometimes that can be computed analytically. So in the Schwarzschild spacetime, it's A equals 0 for arbitrary eccentricity, and in the equatorial plane, then P at the separatrix is equal to 6 plus 2e. So this is returning P at the separatrix. But you can also compute the value for an arbitrary orbit, basically. So arbitrarily inclined, arbitrary eccentricity, arbitrary spin. This is the value of P corresponding to that for the separatrix. And here, just to show off, computed to 40 digits. Okay, so I think that's all I want to say about that. That it's actually a very useful package. I use it all the time in my calculations. There's a bit more it can do, and the documentation is pretty decent on it. I didn't mention actually, but if you put your cursor on any of these functions and press F1, it'll bring up a help page. It's the built-in Mathematica, or looks like the built-in Mathematica documentation, and that will give you some further examples of, and also some of the options that are available for the different functions. And I'll also just finish this section by saying that, as I said, the moment it just does timeline GD6, it'll do null in the future, and unbound orbits as well, so scattered orbits. And there will also be one of our plans for this summer is to kind of hack together a package where the spinnery is spinning a secondary, so where you're solving the Matheson-Papert-Petru-Dixon equations. And so we expect that to appear in the near future. Okay, so if you like that zeroth order perturbation theory covered, let's go ahead and actually look at some perturbations and compute some waveforms. So one thing that's going to be fun for doing that will be making a comparison with numerical relativity. There was a question about the plot. If you miss anything, you can just find it on there's a notebook called BHP Toolkit Tutorial Solutions, and that has the same code for the plot. Yeah, sorry, I just cut and paste that in very quickly because I didn't want to write it all out. It would take a little bit of time, but it's exactly the same code that appears on the actual GD6 package webpage on the toolkit. So you can kind of paste it from there as well. The coordinates are just Boyer-Lindquist coordinates by default. I don't think there's any option to pick anything else. Okay, so moving on. Let's just quickly load a numerical relativity waveform for comparison. So we're going to produce a waveform just for a quasi-circular inspiral. Everything's non-spinning. And we're going to be using something called the adiabatic approximation, where we're assuming that the orbit is evolving very slowly, which in practice means the mass ratio is very, very small if you think of it as the small mass divided by the big mass, or very large if you think about it the other way. And for comparison, then we need to, interesting to compare against numerical relativity simulation. Now, as you know, doing very high Q numerical relativity simulations is very expensive. So above Q equals 10, there are only a few. Maybe Q15. There's a Q20 or 30 floating around out there. A few slightly higher, but typically very short. But here we'll just make a comparison with a 1 to 15, which comes from the RIT public catalog. So you don't have to load anything. This data is already contained inside this notebook. So if you run this cell, that should work. I have heard there can be problems with slightly older versions of Mathematica in loading that data. So hopefully that works for you. If not, you'd have to go find the data from the catalog. That data comes, as all data should, with like this, of a metadata file that gives you the two component masses. So mass M1 of the larger black hole and mass M2. So we'll define those. And then we're going to use capital M in this notebook to mean the total mass, the sum of the two constituent masses. Okay, so to proceed, it's actually going to be useful to talk about different mass ratios. First of all, in our community, we tend to use epsilon, which is the mass of the secondary divided by the mass of the primary. So it's a small number, always less than 1. It's more common in the NR community to talk about Q, I think, where it's basically 1 over this. So mass of the primary divided by mass of the secondary. It's more convenient when talking to people to say Q10 rather than Q of 0.1, for instance. So that's typically used, so not always, but that's how I'm defining it here. And it's actually, we're also going to use the symmetric mass ratio given by this definition here. So given this M1 and M2, we can define those. And as you can see, this is a mass ratio of 15. And yeah, here's the other definitions. Later on, it's going to be useful to define a function nu q, because we'll want to use that later. So I'll just define that now. So it's just nu as a function of q's like that, just as a check. That is indeed the same as we got from this. So in order to make comparisons between waveforms, we want to set up the initial conditions for our perturbation theory waveform as closely as possible to the numerical relativity. calculation. So one way we can do this is we need to extract the initial phase and the initial frequency. So if you do happen to have simulation tools installed, which is a package written by Barry Wardell and Ian Hinder, it's very useful. Then you can run this command here, which will compute, it'll load that and then compute the frequency in the waveform and the phase. But if you don't have that installed, don't worry, you can just use the two values that are given here. This is just the same. And these then correspond, given from this frequency, in terms of our perturbation theory calculation, correspond to an orbital separation given by R0, where R0 is m times the orbital frequency to the minus 2/3 power. So an orbital separation of about 10.8 is the initial. Great. Okay, so we'll show that waveform in a moment, but first of all, let's actually look at computing an adiabatic inspiral using the Black Hole Perturbation Toolkit. So just a little bit of description about this. So what we tend to do in these perturbation theory calculations is we treat the secondary as a point particle orbiting around the black hole. And then that orbit will slowly decay due to the loss of energy and angular momentum in the form of gravitational radiation. And we can certainly, one way to consider this system, or one way to picture what's going on, it's not the only way, but it can be a useful way, is to think of the point particle is following it's not quite a geodesic, like, but in a very small mass ratio sense, so small epsilon. It's very close to a geodesic, but it's slightly perturbed away from it by some force, some small acceleration away from geodesic motion that we call the self force. And so therefore the equations for the small secondary obey the geodesic equation with some forcing term on the right hand side, with this term here is known as the gravitational self force. Actually computing all of the components of this self force is a pretty challenging task, well beyond the scope of this tutorial. And in fact, with the toolkit at present, you could probably only do it for scalar field perturbations, because you don't have access to the metric perturbation necessarily, although that will be coming. So instead, what we will do is make use of a flux balance law to sidestep this and just compute the leading order evolution. This is what's called an adiabatic inspiral. Okay, so at leading order, we get the relationship to the frequency, the orbital radius. This again for quasi-circular orbits. This is going to be the same as what is given by this command, one where we want just the azimuthal frequency. It hasn't simplified it fully, but those are the same. It always returns, the toolkit always returns, if you like, effectively where capital M is set to 1. So sometimes you have to put that M back in where that's appropriate. We can then, avoiding all that calculation of the self force, we can just use the chain rule to get an evolution for the frequency. So d omega dt is d omega dr naught. We have that equation times dr naught by de. Well, that's just 1 over de by dr naught. We can get that as well, times de by dt. And then we'll go ahead and relate that to the gravitational flux. So again, we can compute that just from what we have in the toolkit. We can do d omega r naught times the Kerr geo energy of 0, r naught 0, 1, minus 1 times E dot. So that's the equation for the evolution of the orbital frequency. And if you like, it can be useful to simplify that a little bit. It's not just with the assumption that R0 is bigger than 2, and see it's actually quite a simple equation. So this is telling you how the orbital frequency evolves as a function of time. This E that appears in this equation is the energy of the body. And as long as the system is evolving slowly and everything's evolving adiabatically, we can replace E dot with minus the flux of gravitational waves. And so d omega dt 2 is just going to be d omega dt, where we replace E dot with minus F gravitational waves. So that's our final formula for computing the orbital frequency evolution. And so this is a very simple differential equation that we can solve for omega once we know the flux, which we'll compute using the Teukolsky package in a moment. And then once we know the evolution of omega, we can just integrate that once more to get the evolution of the orbital phase. So d omega 0, where omega 0 is the orbital phase, by dt is just equal to capital omega. So that gives us the inspiral. And then what we can do is we can write the waveform in a form where it's factored into an amplitude. So here we have our usual h. That's h plus I h cross. So this is a complex quantity. We can write this as a sum over spherical harmonic modes in this case, as some amplitude times e to the im phi 0, where phi 0 is the orbital phase. And this amplitude is not necessarily real, but it's always complex. If you like, it's the tail terms, if you know about PN theory and things appearing inside here. And this is what we'll compute from the Teukolsky equation. So that's the things we need to compute. So we can see from above what we need is the flux of gravitational waves. We're going to need these amplitudes as well. And all of this for a point particle on a circular orbit. And the packages that appear in the toolkit make that very easy to do with the current setup. Okay, so let's go ahead and compute the energy flux and the asymptotic wave amplitudes. So actually, we're working in Schwarzschild in this particular case, so you could use the Reggie-Wheeler package, but let's use Teukolsky because it does extend neatly to rotating black holes, and everything that I'm saying here would work straight away for circular equatorial orbits about a rotating black hole. So first of all, we'll have to load the Teukolsky package, same as before, double arrow Teukolsky, and then the backtick is crucial. And you run that, hopefully that just works without any issues. Just as an example, let's compute the 2-2 mode of psi 4 for a circular orbit of radius r0 equals 10 about a Schwarzschild black hole. So let's just set up the parameters first of all. So for psi 4, that's a spin weight -2 perturbation. The package will solve for arbitrary spin weight. Certainly between -2 and 2, so -1 and 1 and 0. I'm not quite sure what happens if you run 3 or 4. I'm not sure what reason you'd have to. We'll say L equals 2 and M equals 2. So that's the modes that we want to solve for, and the spin weight of the field. We're going to set A equal to 0. So that's the Schwarzschild case. We don't want any eccentricity. At the moment, we can't actually use it. And we'll also set the inclination angle to 0, so it'll be in the equatorial plane. The package, although it doesn't yet do it, is set up to deal with generic orbits. So it knows it has arguments for the radial harmonics and the polar harmonics if you were doing more generic calculations. We're not, we're just doing circular orbits. So we set these harmonic indices to 0, so K and N. And then we'll set P, which is the same as the radius in this case for circular orbits, to 10. Now I'm going to set it with high precision because the internal workings of the package at the moment, or at least the way I'm going to show it to you, actually requires high precision input, because the package will use the precision of the arguments that you pass to it as the precision it uses throughout the calculation. And if you use just regular machine precision, it actually sometimes can fail. So that's a slight downside at the moment. We will work to fix that in the future. So we'll set those parameters. And the mode frequency is given by m times capital omega that we computed before. Okay. So as I said, we will need to actually compute one of these orbit functions in order to pass it to the Teukolsky package. So A, P, E, cosine theta inc. So go ahead and compute that, and you can actually see it gives a little picture. It's a little circular orbit. And then solving the Teukolsky equation is now extremely easy. We just do Teukolsky, in this case, Teukolsky point particle mode. This is for a point particle. We have a spin weight S. We're looking for the L equals 2 mode. We have these N and K, which is set to 0, and then we pass the orbital configuration. So when we run that, that returns, again, one of these Mathematica objects, something that you can query for various results that you might find interesting. And you can actually expand that and see there's some further information that it gives you there. Put that here. Okay, so from Psi4, we can immediately get the energy flux, for instance. So that's the flux of radiation to infinity through square plus, and the flux of radiation passing down into the black hole for this mode. And we'll just give that a name, F22R10. So the flux for the 2-2 mode. And we can also obtain the metric amplitudes. So Psi4, and if you ask it the amplitudes, in this case, we want the amplitude of the gravitational waves to infinity. And we'll get this. So again, if you just do the amplitudes, it'll give you the amplitude of the perturbation at infinity and at the horizon. To extract the infinity, we just ask it for the key sky plus. And this is Psi4. We actually want H, because we're in the frequency domain. That's easy to compute. That turns out to be a factor of 2, but then there's a omega squared appearing here. I guess. Okay, just set that to 10. H22R10. So that's it. That's how you compute the flux per mode and the amplitude associated with that mode. Now, obviously, I can go ahead and compute all the other modes. We need to compute the flux typically up to, say, L of 10 might be good. And you can run the toolkit to do that. It's a mathematical implementation. It uses extended precision. It's not incredibly fast. But to save time, that this has already been done for us. So this data was pre-computed, and then it's being interpolated here. So here's the flux, and here's the amplitude. So you can just double check that this amplitude from this object, this interpolation, at all these different values of R0. So this is an interpolation over the LM modes and R0, and this is an interpolation over R0. And we can check that our flux that we computed why do those two things not agree? Apologies, those two numbers should be the same. They were in my example notebook. Okay, maybe I've made a small typo somewhere, but this data, the pre-computed data is fine. So we can not worry about that too much. Okay, so let's see how we're doing on time. Yeah, pretty good. I think what I'll do here is I'll just cut and paste in the solving of the inspiral and just talk through it rather than write out all the code. So here, Mathematica has a command called ndsolve, which is just used for solving differential equations. And from the equations we had above, we have some very simple equations. this is the evolution of the orbital frequency. This then is the evolution of the orbital phase. This is the definition of the frequency. And we're going to start our inspiral at the same values of R0 and phase that we extracted from the numerical relativity waveform. And we're going to integrate until we get close to the ISCO. So the ISCO is at 6 in the Schwarzschild case. And we've set some precision here as well. So we're just after 10 digits of precision, basically. It's going to be useful. So that's gone ahead and done that. To also get the initial time, which we set to be 0, but also the maximum time. So this calculation stopped when we got close to the ISCO, and so just so we know what time that is, so we can make our plots. Tmax is at 2000, roughly 2,100 M. Okay. So we can do things like plot the evolution of R0. Let's just give it a plot beam. T min to T max. So there's the evolution starting as we did at 10.8 until we get down to the ISCO. And we can do, of course, exactly the same now because we've already solved this for our orbital frequency, which has a different name, just omega sol. So this is the frequency evolution as a function of time. And likewise, you could do the same for the phase evolution, which again is just phi sol. So there's the evolution of the phase. Okay, so that's our inspiral. That's what we computed. Want to then take that as input and actually compute a waveform. So let's define the waveform function based upon the amplitudes that we had before. So h as a function of time is equal to, in this case, the symmetric mass ratio, because it turns out that using the symmetric mass ratio improves the comparison with numerical relativity. So that's what we'll do. Minus I m by sol t, and then there's some initial offset we have to get right as well. So initial phase coming from the complex amplitudes. So it's just defining the waveform as I wrote it out above. And now what we can do is we can plot this waveform alongside the one we had from numerical relativity. So first of all, let's plot the NR waveform. We didn't do that yet. Let's just make that bigger and a bit nicer, detailed. So that's the numerical relativity waveform. And we can now plot the one we got from perturbation theory. H of t, t from t to t max. And this plot style, let's plot a different color as red. Let's just make the image a little bigger. Let's see. T min to T max. That has not plotted anything. That's because these functions have small s's, not capitals. There we go. So in blue, we have the numerical relativity calculation, and in red, we have the result from using the adiabatic waveform computed using the Teukolsky package. And you can see, initially things are phase aligned, but then they reasonably quickly obviously drift out of phase. And that's not surprising. What we have here is a real abuse of perturbation theory. We're using it at Q equals 15, a mass ratio 1 to 15. That's depends who you ask, but that's not really a small mass ratio that you would expect. So it does okay, but then it does drift out of phase. That's not unexpected. But you can see, though, hopefully, that it was very easy to compute that waveform. It's just a few lines of code. You'd have to run a little bit over the L and M modes and over the R0 values, but it's pretty straightforward to compute them, at least for the quasi-circular case. Okay, I will just take a moment to talk about what's just 5 minutes to talk about what's happening in perturbation theory, and it really is also one of the motivations for extending the toolkit. So what we saw above was what's called an adiabatic waveform, but there's been recent progress on computing post-adiabatic waveforms. So extending perturbation theory beyond linear order in the mass ratio. So taking the metric of the binary to be some background metric, in this case, the Schwarzschild metric, plus the first order correction in the mass ratio and a second order correction. What we just did above was solve for psi4 related to the first order perturbation, and then computed the metric just at infinity for the amplitudes. The actual calculation of this second order metric perturbation is substantially more involved. It's taken many years of work, but has recently been completed in the quasi-circular case. The way that proceeds is actually we write these metric perturbations as a product of a slowly evolving amplitude and a rapidly evolving phase, and these slowly evolving amplitudes evolve on what's known as the slow time or the radiation reaction time, and the phase evolves on the fast time, and we can use that to perform what's called a 2 timescale expansion. We can then substitute into the Einstein field equations. Everything can be expanded on the basis of tensor harmonics, and there's some regularization procedure as well that's very important that I won't discuss. In the end, though, what you're left with is a set of coupled ordinary differential equations sourced by some non-compact source, which is formed from quadratic combinations of the first order metric perturbation. So to compute second order things, you need data from the first order metric perturbation everywhere in the spacetime. This was again a motivation for building the toolkit, is to make it easy to compute that data. I'm not going to say very much after them to say after many years of work, we have actually managed to solve these equations, and they're not quite on the scale of NR for sure, but I would say the calculation of the individual modes. So you want to compute the 2-2 mode at 1 radius would take a couple of days on a 40-core machine. So it's substantially more computationally expensive than what we just saw above. That said, though, the code is certainly not optimized, so I'm sure there can be savings made. If you're interested in this sort of stuff, then the results are presented in these recent letters. But just to give you just a one figure summary, here is the comparison, it's expanded, between a numerical relativity waveform. Apologies, it's an SXX waveform in this case, but one done at Q equals 10. That's the black waveform in both of these. The blue curve is the adiabatic waveform we just computed above. It's exactly that, no different. And then once you add on these post-adiabatic corrections, you see you get this really nice agreement with numerical relativity up until close to merger, where our 2 timescale approximation breaks down. But it does really quite remarkably well, even at mass ratios of 1 to 10, which is, you might think of using perturbation theory, but it seems to work remarkably well. I mentioned that because it is the next big thing, I think, in perturbation theory. And in terms of the toolkit, what we plan to do in the coming year or so, I would say, is really open up a lot of that code so that other people can improve upon it and make it better, make it more efficient for one, but also make their own post-adiabatic calculations for these kind of, more intermediate mass ratios, Q10, Q20, Q30, that kind of thing. So something to look out for appearing in the toolkit. Okay. So that's what I want to say about numerically computing waveforms. I want to spend just a little bit of time now looking at working with post-Newtonian series and using those to compute inspirals. And that will lead on, if we have time, we'll do eccentric case, and that will lead on neatly to this, this Python package, the Fast EMRI Waveforms package. So in addition to code, as I said before, the toolkit also stores data. Some of that can be numerical. As Barry mentioned, the very large numerical data sets go on Zenodo, but the analytic data sets, such as regularization parameter, in particular post-Newtonian series, typically stored in GitHub. And in the case of the post-Newtonian series, there's actually a package as well. There's a Mathematica package that's wrapped around it for actually computing, for working with those series, because they're large and they can be quite helpful. Let me just shrink that down again. Okay, so as before, we have to load the package. So post-Newtonian cell force is how it is loaded, all with camel case on the PN, S, and F, and the backtick. And there are many PN series in here. I will just load one of them to start with, and then later on look at the other ones that are available. These are sort of categorized in a directory structure, so it's quite clear what's going on here. I'm loading the Schwarzschild PN series for circular orbits. I want the flux to infinity. I also don't want the L modes. I just want the total flux. So an exclamation mark here says don't search for anything with the for the individual LM modes. Oops, sorry, there should be a slash. So this will take a second to load. It actually seems remarkably dependent on your version of Mathematica. Sometimes it loads instantaneously. Some version it seems to take 10 seconds to load, and we're not really sure what the difference is, but it shouldn't take too long. Once it's done, we will get access to a PN series. Just give that a second. There we go. Okay, that took a little bit longer than I expected. And there's a little bit of extra data there. You can actually see this is a very high order post-Newtonian series. It starts at basically x to the 5 and goes to x to the 28. So it's a 22.5 PN series actually in this case. So once you have this object, this post-Newtonian data object, you could ask it for various things. I'll show you later a couple of other things you can query it for, but probably the most useful thing you want is actually the series. Now, if you just press Shift Enter on this, it'll try and print out the whole series, which is vast in scale. But you can truncate the series at any order you want by just adding on using Mathematica's big O notation. So this thing is a series object in the pure sense in Mathematica. You can use O, not y to the 8 as an example. So there's the first few terms, but just as easily I could have asked for y to the 15. There's the first bunch of terms, and that is just the beginning of it. It goes all the way up to y to the 28. So again, it's the kind of thing that people would say they'd computed, but you might get some auxiliary or ancillary material with their paper that would actually give it in digital form. But if they ever just put it in tech, you are never going to type all this in and not have a mistake. So it's useful to have them all in one place. Okay, we don't want to look at all of that. So let's just keep that short. So let's define a function. So we're going to use something very similar to what we did before. but we want to evaluate our post-Newtonian series at some value of R naught. As it says above, the post-Newtonian, this inverse separation parameter y is defined in this invariant way as m times omega to the 2/3 power, which is also equal to m divided by R naught. So we can define a function like this, e dot pn, pass for that series plus, and we're going to truncate that series at some power n, based on what we ask for in the function. We don't want it to be a series anymore, so mathematically you take it to be normal to convert it to just a polynomial, basically. And y you can just write as 1 over R naught. I'm just going to take m to be 1 in this case. Okay, so once again, I'm just going to, actually what I'll do, if it's easiest to show, I'm just going to use exactly the same code I used before. But instead of computing an inspiral using a the numerically computed flux, we'll use it using a post-Newtonian computed flux. So here we'll replace these with Pn. My flux is now flux Pn, but nothing else is going to change. But what I would like to do is I'd like to run this for many different truncation orders of the post-Newtonian series. So for different values of n, so truncating at different orders, so we can look at the convergence of the series. And so then I'm going to get a whole load of these. I'll wrap this then in the do loop. And 6 to 20 in steps of 1. And I don't think this takes too long, but we can just monitor that. New is defined. Oh, sorry, this is incorrect notation. It's R0 of t, and it's this function that has 2 arguments, not this function. There we go. So there we go. It just computed a whole series of post-Newtonian inspirals using different truncation orders of the Pn series. So what we can do is we can plot R0 Pn for some n, let's say, function of time t from 0. We'll also need the maximum time. So that needs to be inside the loop. Because the time it takes to get the ISCO will vary with the post-Newtonian order. So just put in a t max Pn in here, which just reads off the maximum time associated with the solution. So from 0 to t max Pn n. And again, we can manipulate this, varying n from 6 to 20 steps of 1. R0 Pn. The T max. There. Okay. And we might wish to compare this against our numerical solution that we had before. T from 0 to T max. And let's give that a different style. dashed red. Okay, so the dashed red curve here is the radial evolution that we computed numerically, but using the PN series, you can see just using the leading terms. So if you truncate with just order 6, you see that's just the leading quadrupole term. But we can add more terms let's do a plot range all on that. As many of you might know, adding more terms on the PN series doesn't necessarily mean, or adding the next term doesn't necessarily mean things get better. And in fact, we see that quite clearly here. These two curves aren't too far apart. We add the next term, they get further apart. So adding one more term in the series makes it worse. Adding yet another term, it's even worse. Just because the convergence of the PN series isn't great. But as you keep adding more terms, suddenly you add the next one, it gets very good. And in fact, as you keep going, it oscillates around. And by the time you add a great many terms, you see it actually agrees beautifully with the numerical result. So this is something we can do in perturbation theory. Normal PN, where they aren't just expanding at linear order, the mass ratio is restricted to 3.5, 4 PN. They're working towards 4.5 and 5 in different places. But here we actually have these really high order post-Newtonian series. So we've analytically captured a lot of the numerical result by having such high order series. And I'll just cut and paste this in the interest of time. It's exactly the same as we had before. Just going to define some waveform based on the PN series. Here, I'm just going to use the amplitude, the numerical amplitudes. We don't actually have the PN amplitudes in the toolkit at the moment, but I'll use the phasing from the PN series and the radial evolution as well to define this function. And again, just to save cutting and paste, it's all basically the same. Where's the PN series not appeared there? Let's just see HPN 06. There's an M in there. We'll just make that the 2-2 mode. There you go. Okay, so as we saw, so what's shown here, we have the full first order in the mass ratio perturbation theory waveform in blue, and in red we have the PN series. And just as we saw with the radius, as you add more terms, it briefly gets worse. But as you keep adding terms, eventually you find you get beautiful agreement. So once you've got something like 10 PN, at least in Schwarzschild, you can basically get a waveform that agrees very, very nicely with the numerical waveform, right down to the innermost stable circular orbit. So this is cutting off at R0 of 6.01. So it shows the value of having these big series. Of course, they're analytic, they can be evaluated often quite rapidly. Okay, so that was everything we've done so far has been quasi-circular. Let's take a little look at how you would do things for eccentric orbits. Now, as I said, at the moment, the Black Hole Perturbation Toolkit doesn't actually contain any code for computing, say, the Teukolsky fluxes for eccentric orbits. It is coming soon, both in the Mathematica package, and also Scott Hughes is kindly donating his software that he's been using for years, which works for fully generic orbits around Kerr spacetime. So that should be in there in the not too distant future. So in lieu of actually having numerical fluxes, what we'll do is use post-Newtonian fluxes. So hopefully this, I got 34 minutes, yeah. So we'll see how this goes, and then if I need to cut it short, I'll move on to the few stuff. Okay, so this is clear out some parameters we've defined before. We now need to change up everything and actually compute various quantities now for eccentric orbits. So we need the energy and angular momentum, for instance, for eccentric orbits. We saw at the beginning how we could compute those analytically in terms of P and E. So that's those two there. And to get evolution equations for P and E, we can use these equations here, just using the chain rule. So we can just write those out. E dot is equal to D En comma P dot plus the derivative of E with respect to the energy with respect to eccentricity, E dot. And then we have another equation, L dot is equal to derivative of L with respect to P dot plus the derivative of L with respect to E dot. So that's our system of equations. And we can just solve that then. Oops, let me take double equals, not one. That's going to cause problems. Just clear that assignment. We can solve that for P dot and E dot. So that's there. They look kind of messy, but we've just all simplified them. Yeah, so they're not too bad. So those are the equations of motion that we want. So this is the equivalent of the evolution in omega before. So now we have the rate of change of similar rectum and the rate of change of the orbital eccentricity. And just as before, all we need to evaluate this is the energy flux. So, and in this case, also the angular momentum flux. So we, as I said, we don't have access to, well, from the toolkit, you certainly can't compute those just yet, but we do have post-Newtonian expansions for these. So I didn't mention this before, but there's actually a lot of post-Newtonian expansions available. So if you just run the post-Newtonian expansion with no arguments, it gives you a list of all the series that are currently there. And in fact, you can see there's about 60 high order post-Newtonian series that are just available for you to load. Okay, so let's actually go ahead and load some of those. So we want, in this case, Schwarzschild, eccentric, the flux, and the energy to infinity. Once again, I think that's going to take a little bit of time. And the same with the angular momentum radiated to infinity. So these PN series, we endeavor to keep them up to date. And so you can actually, the PN series, over the years, people have extended it from 5, 6, 7 up to these very harder PN series. If you ask each of these objects for a reference, it'll tell you. So references might be more than one. The paper where this most recently came from. So this PN series is quite recent, coming from the this paper in 2020. And the authors of that are the Chapel Hill group. And you can see we have a PN series up to 9 PN. Just as before, we can query the PN series, to actually get the series itself. And just as before, this series is absolutely vast. In fact, it's even more vast because now you have an expansion in eccentricity as well. So that's just the leading term, but very quickly, it'll start to get quite large. So just the first 3 terms are already pretty big. As you can see, that's because, not only do you have y, and now each y isn't just an integer, also factors of pi. We also have powers of e and e squared, and there's some singular factors here as well. Singular when e goes to 1. but that's fine. You'll also notice there's some other slightly funny series in here. We'll have to deal with those in a moment. Right, but before we do, in order to evaluate this y is still defined the same way, but now this omega is the omega for an eccentric orbit. So we'll need to do phi eccentric equals Kerr geo frequencies 0 p e1. I take the omega phi, so that's the frequency for an eccentric orbit. Not too complicated, but it's not trivial either. Okay, and before we can evaluate this series, we also need to define these functions. So this is done, the tutorials in this package will show you how to do this. You have to call this command. It won't seem to do extra functions, sorry, it won't seem to do anything, but it has the purpose of defining these functions. We'll need to do that for both of the two PN series. So there's those defined. Okay, so now if we take a look at the PN series, I'm going to define it in the following way. It's going to be useful. See why in a moment. So there's the series. So this function has been defined, but it's still not evaluating. And the reason for that is that there's actually a hold stopping this function being evaluating, because often you want to look at the series without that happening. If you look at the full form of this, let's see if this is going to make sense. You know about Mathematica, you can see there's a hold form that appears here, so that stops this being evaluated. If you don't know what that is, don't worry, but it's just Mathematica as a way of saying don't evaluate this just yet. The way you can get rid of that is by using a release hold. That'll give you an error because we also need to define this highest power. So the reason these functions are here is that they're known to be very easy to compute to arbitrary order in E. And so if you want to compute this to E equals 10, that's very easy. So to do that, though, we have to just say the highest power equals 10. And there it has now replaced that function with this expansion up to e to the 10. Okay, so that's a prototype for a function we're going to want. First of all, we don't want it in series form. We want it in a way we can evaluate easily. Just keep that like that. Okay. E dot PN, we'll just give that another name. And we'll take that, we'll get a few terms in the series, but not too many. And we need to replace Y with omega phi eccentric to the 2 first power, again, just setting capital M to 1 in that replacement. Okay, that took a little bit of time, but that's fine. It's just has to do it once. Again, now the angular momentum, exactly the same, just with L dot. But the L dot series, this is actually quite crucial, starts at a different order. So the reason I'm doing this is that this series starts at y to the 5, and this series starts at 7/2, y to the 7/2. It's quite important that actually when you truncate these series, you truncate in the same order together. So this is equivalent to going to 7pn, or 6pn, I suppose, in both of these. If you truncate one to 3pn and the other one to 9pn, sometimes you find very strange things happening, like the orbit can actually grow when it shouldn't, or the eccentricity should increase when it shouldn't, and things like that. Okay. And in order to actually then compute a little inspiral, we will need to define a function like this. P goes to P1, E goes to E1. That's the way I've set this up. Just check that works. There you go. So that's now evaluated that 6pn series for those two values. We'll do the same for L dot. Okay. In the interest of time, as I would like to just have a few minutes on the view package as well, I'm just going to cut and paste this in. These are just the equations of motion. And this then should give the phase space trajectory. So the evolution of P and E through the space. Obviously not. Consistent with these initial conditions. Apologies, I'm not quite sure why that hasn't worked. I worked an example this morning. The eccentricities are all defined just fine. Okay, I think I'm just going to leave that there just in the interest of time. It's slightly unfortunate. It's the solution notebook has it all. What I will do, as I have it open here, as my kind of crib sheet, what we were working towards is actually computing the actual full evolution, the inspiral, so the in physical space. So that inspiral should have corresponded to something like this, where we have the motion in the XY plane, the non-spinning black hole. So apologies about that. I'm not quite sure what went wrong. But as I see, I'm actually running down on time. I only have 20 minutes left. What I will say is, you can do that calculation, but of course it is restricted by the PN series. That's restricted. It's it's not great in the strong field. It's a reasonably high order series. In this case, up to 9th PN. But for strong field results, you want to do better than that. And it's also restricted in the order of eccentricity. It goes to the. You saw the expansion we have here in powers of E. That expansion doesn't converge very quickly either, and so you actually need many powers of E in order to get something to be particularly good, as say E eccentricity of 0.5. So of course you'd like to do this numerically instead. Fortunately, there's this other package, the Fast EMRI Waveforms package, which does all of this for you and does it extremely quickly, and allows you to compute waveforms that are good enough for Lisa data analysis. I'm just going to show you that now for the last 20 minutes or so. So I'll just share my screen. Okay, so this is one of the notebooks that is shared on the webpage for the Einstein Toolkit workshop. So again, there's a solutions one which has everything already coded up that should work, and I'm just going to go through a few examples. Let me make the text a little bigger. Hopefully that's more readable, at least the code is. Okay, so yeah, hopefully if you want to use this, you've had a chance to install it. This tutorial is just a very short, small subset of what it can do. This package is mostly the lead developer written is Michael Katz. He's done a really impressive job of building a very modular package. It's really well documented as software goes. And so if you want to use this, then I'd actually recommend just looking at the main tutorial there. It's very extensive and very good. So here I'll just give you a flavor for what you can do. The other really amazing thing that Michael has done is the package basically seamlessly will work with CPUs or GPUs. So if you have GPUs available and you have CUDA installed and all that kind of stuff, you can just basically set a flag saying, I want to use a GPU, and it'll compute all your waveforms on GPUs instead. Now, if you do it on CPUs, the waveform will take, for a year-long waveform, sampled every 10 seconds or something, it will take 10 seconds or so to compute a waveform. But if you do it on the GPU, it'll do the same calculation in about 0.1 seconds. So it's very rapid, and that is fast enough for Lisa data analysis. Okay, so just a couple of basic things, the usual, load NumPy, matplotlib, and just set some parameters to make the fonts, the figures a little bigger than the default. So just to start, before we think about anything else the package can do, probably the most common thing people want to do with it is just generate a waveform. So let's just take a look and see how that can be done. There's a generic interface for it. The details are given here to these references about how the waveform's actually computed. There's a letter and a follow-up paper giving lots of details about the model. We are computing fluxes. We're interpolating those across the space. The waveform amplitudes are then interpolated using a reduced order model neural network, basically, using some clever interpolation across time to produce these very rapid waveforms. Okay, so we need to load a couple of things. So we'll import generate EMRI waveform and also fast Schwarzschild. What's it called? Fast Schwarzschild eccentric flux. So this generate EMRI waveform is a very generic interface for computing EMRI waveforms. And this is a particular model, the relativistic one that uses just the adiabatic fluxes in order to compute the waveform. The next one, GenWave, generate EMRI waveform. We use that interface and just say this is just basically telling it we want to generate this sort of waveform. Now, if you're running out for the very first time, it'll go ahead and automatically download all the necessary data, I think, from Zenodo, so maybe 100 megabytes. So it might take a little bit of time. It just downloads everything you need for the neural network and does it all for you, and it should just work seamlessly once the download's finished. Again, in the interest of time, because there's a lot of parameters to describe these waveforms, what I'll do is just cut these in and explain them. So we just set a bunch of parameters for the waveform generation, of course. The time is specified in years. We're going to do a time spacing of every 15 seconds. We can set the mass of the big black hole in solar masses. We can set the spin. This is actually ignored in Schwarzschild, so it doesn't matter what that is. The model won't take any notice of it. We can set the mass of the small black hole. We can set the initial P, the initial eccentricity. We can go to eccentricities of a little more than 0.7. I think 0.75 is okay in the model at the moment. Inclination will be ignored. And then there's a bunch of viewing angles and angles of the source relative to the observer that you can set, as well as some initial phases. And these last two are, sorry, this one here will be ignored in the generic case. So we can just set those parameters. And then again, to save typing it all out. And again, you find this in the solutions notebook. We can just generate a waveform. You can see that's running, but it's done. So that was it. That's all the time it took on my laptop to generate a year-long EMRI waveform for a high eccentricity in spiral. So we can now plot these. So the real part, say, the first 2000 time samples. Don't know why that plot's not come up larger than, would have thought that would make it large. There we go. And of course we can plot the imaginary part as well. So there you go. That's a highly eccentric waveform. So eccentricity 0.7, you can see these big peaks every time that the periastron passage is made. And that's just plotting the first, let's see, if we have 15 seconds, we've got 2000 we've plotted, divide that by, there you go, so it's the first 8.5 hours. Yep, of data you'd expect in Lisa for an EMRI. Okay. So yeah, this has already done all that stuff that the toolkit could do for you or will do in the future. It's already done the flux-driven inspiral and the waveform. Okay, something else we might want to do. So this, I should say, this waveform includes modes up to L equals 10, I think. It includes radial harmonics of plus or minus 30. We'll see an example of that. What it means to use less than that in a moment. But something you might want to do is see, well, and a question we answered in one of those papers is how well does it work if you just use the 2-2 mode? Right, it's the dominant mode, but how much are you losing by just doing that? To do that, to compare two waveforms, we want to do computer mismatch. So we'll import this function, get mismatch. And looking at the waveform just for this purpose, you get a little bit more control over the model if you just work with it directly rather than using the generic interface. Flux. So now we don't need to worry about all the sky positions. In fact, this is going to keep the waveform in the source frame. So we don't need to worry about any of that. We'll once again just set the parameters. So total mass, the mass of the small body, initial parameters, these sorts of things. This is the viewing angle from the source frame. I should have said before that the previous one is computed in the solar system barycenter frame. And then E naught eta by distance equals that, dt equals dt, dt equals t. So that's actually just computing the same waveform we just had before. This time for just 0.1 of a year, but in the source frame. What we can do,
10 minutes.
Just 10 minutes remaining. We can compute just some modes of the model. It's 30 to 31. So this is the radial harmonics. So there was a question in chat about what n meant. N is the radial overtone index. So we can play around with this in a moment and see what that effect that has on the waveform. And you can go up to 30, plus or minus 30 in the current model. So here we're just going to look at the 2-2 mode. So it has exactly the same set of parameters with an additional argument called mode selection equals specific mode. So the modes we've chosen before. And now what we can do is plot that should work. Wave underscore base. So there's the waveform that includes all the available modes. You can see there's some small oscillations on the waveform. When you look carefully, that's actually coming because we've truncated the radial harmonic sum at plus or minus 30. If you added more, these would vanish. But for the purpose of the model, this was sufficient at the time. And if you just plot the 2-2 mode now, you can see it's pretty good. It's pretty close, but it's not exactly the same. The higher modes do have an important effect. This is probably more pronounced at the end of the waveform. This is just at the beginning when you're more in the strong field. And something else we can do is we can then compute the mismatch between these two, assuming a flat noise. And you see it's not terrible, it's not perhaps not great either. So just compute the mismatch between those two waveforms for 1/10 of a year. Okay. So to conclude then, I will just do a couple of things. I will just quickly look at the phase space trajectory. So unfortunately, it didn't work in the Mathematica notebook. I made a mistake. But if had it done so, then we would have computed this trajectory using those PN series. But you can do it here as well. So now we can, from view, import the trajectory module and the inspiral. What's called the EMRI inspiral. The trajectory is given by EMRI inspiral func. The function is going to be the Schwarzschild eccentric flux. And once again, we'll set some initial parameters. And yeah, in the interest of time, I will just cut and paste this in. There's this trajectory function which will return all these other this other data. And then we can plot, for instance, the evolution of P and E against each other. So here we've started an eccentricity of 0.5, and we've evolved until we've approached the separatrix. There's this little uptick in eccentricity that's well known in the EMRI case that we see. And if you like, you could go back and compare this to what appears in the Mathematica notebook where we did the same calculation with the PN series. So what View is doing is exactly, or this particular model from View, this Schwarzschild eccentric flux, is exactly the same as the calculation that I was trying to do in the Mathematica notebook, but just using numerical fluxes rather than post-Newtonian fluxes. But it's exactly the same equations that I derived in the notebook. Okay, and I think I'll just finish by just saying, well, we don't yet in View. View is designed, as I said, to be very modular and to accept kind of all future self-force and perturbation theory corrections, and then
5
waveforms
minutes.
very rapidly from them. And we don't yet have relativistic models around rotating black holes, but what we do have is these things called kludge models, which use some PN information, some numerical data to produce waveforms that are phenomenologically correct, where the phasing wouldn't be the same as the real phasing. That can still be very useful though for doing data challenges. So one example of this is what's called the augmented analytic kludge, the AAK, that was recently upgraded to use 5 PN information for generic orbits. As I've only got a little bit of time, I will once again just cut and paste that in. It's exactly the same, just using the generic interface, setting a bunch of parameters, generating the wave in exactly the same way as before. And then I can plot the waveform for a completely generic orbit around a Kerr black hole, given those orbits. And that was the beginning of the waveform And you can plot the end as well. So you can see it evolves significantly from these very high eccentricity spikes that appear in the waveform to these very low, this low eccentricity system towards the end. So I think that's been plenty. It's been quite a tour de force of some bits of the toolkit. There was a lot more I have not talked about. I didn't talk about any of the quasi-normal mode packages. I didn't talk about a lot of the Mathematica packages. There's a lot else there. So I think I'll finish there and take any questions if anyone has any. Thank you.
Great. Thank you, Niels. Any questions? Any questions here in the room? Oh yeah, please.
Maybe I have a question. So a significant portion of the toolkit is Mathematica, which is of course and costs money. But there's also a big component, as you're showing right now, which is Python. Is there any discussion about this, about moving towards a like an open source backend like Python, Sage? Or, I understand there's a lot of code that is Mathematica, so of course.
Yeah, that's an excellent question. I mean, I think like Barry said, we're happy to accept code. It's a matter of just having people to write it. It's always great when code is open source. I think the way the community often works, at least within our group and a few others I know, is that we prototype a lot of stuff in Mathematica, but if you actually want to generate significant amounts of data, you're forced to move into Python or C and C++. And so I think that will naturally come. You'll start seeing more and more codes coming in C, in C++, in Python, in Fortran, Julia, other languages that people are really interested in that are much more efficient. I think I might, I did all the calculations with the Teukolsky package in Mathematica just because that's kind of easier to work with, especially in a tutorial format. But you could do all of that with the Gremlin code, which is a Teukolsky solver, which works with circular orbits, which is in C++. And so you could do all of that already with that. And I think, at least for the Teukolsky solver, there will be, the two of those will progress together. You'll have a generic Teukolsky solver for generic orbits in Mathematica. But you're never actually going to compute all the flux from a generic orbit that way because there's 30,000 modes for every point in the parameter space. It's just too slow. So you're always going to have to use a C code eventually if you're doing any sort of practical work. But for looking at just individual modes, Mathematica can be very useful.
Cool. So we have an online question. Hassan has his hand raised.
Great.
1 minute.
Hello, thank you, Niels.
Hi.
I have a question actually about the FEW code and about the waveform precision. So as far as I noticed, the precision of waveform is depending on the precision, I mean, the number of float points for the input flux data that it uses, right?
In the FEW model?
Yes.
30 seconds.
I mean,
yes, that's correct. So the model uses the flux and it's interpolated to a certain precision. That precision is not good enough yet for Lisa, but it's a good first pass, I would say.
Yeah. I wanted to ask, so what is the criteria? Is it something that you decide where to cut that? I mean, the number of load points? Because when I'm
at the
using
moment, sorry, yeah.
No worries.
I would say
when
at the
I'm using
moment,
a new flux data, for example, because I did kind of, I'm using FEW to calculate waveforms for the scalar case, right? So, and so then, for example, for the new flux data that I'm using, the mismatch between the new function that I defined with the normal one in the FEW is, I don't know, 10 to the minus 8 mismatch still. It's good, I guess, but I was wondering,
sounds very good.
When can I say it's good enough? 10 to the minus 8 is good or not, or just I do have to take care of that, I mean, relative to the effect that I'm studying.
So that's a question for whatever you're trying to do with it. So the mismatch needs to be as small as it is to do the science you want to do. So I can't answer that question for you. 10 to the minus 8 sounds very small. So if that's two waveforms you're comparing, that sounds great. But it depends if you're doing it for parameter estimation or something, depends how you want to estimate those parameters. So I can't answer that question. But I would say the fluxes in FEW are just sort of arbitrarily probably about 10 to minus 4 or 5. In
Right.
practice, they need to be at least 1 over the mass ratio in order to get an accurate waveform across a radiation reaction timescale.
I see. Thank you. Yeah, basically because I was wondering that to get a zero mismatch between the new one and the old one, because I'm using the same flux. When so the new one has for example, additional parameter, and I'm putting that to 0, so it should be the same as the normal function in the
I see.
That is what I mean. But
There's
because
a question
the
of
number
why
of,
it's slightly different. If it's a slight difference and you're concerned about it, you could raise it as an issue on the issue tracker on Git, and we'd be happy to take a look.
yeah, sure. So, but essentially, it's just arbitrary. I mean, number of float points that you can choose how many float points for the flux input to consider, right?
Yes, I think so. If I understood your question,
Yeah.
but we can follow up afterwards.
Sure. Thank you.
All right, well, that's all we have time for. Thanks again, Niels, for a very nice overview. And